Okay, everyone should be in now.
Okay, so good morning, everybody. Welcome to this week's Optics and Quantum Electronics seminar. It's a great pleasure to introduce our speaker for today, Professor Florian Marcotte. A little bit of background, Florian did his PhD in physics in 2002 in Basel, where he worked on spin physics, and then went to Yale as a postdoc, then became a junior research group leader at the Ludwig Maximilian University in Munich, and then joined Erlangen first as a full professor, and since 2016 leads the theory division of the Max Planck Institute for the Science of Light in Erlangen, Germany. Many of you have seen some of his work, especially, for example, in my group and in machine learning, but really his work covers some pretty broad spectrum at the intersection of nanophotonics and quantum optics, with particular research topics on cavity optomechanics, topological systems, quantum many-body dynamics, and interfaces between machine learning and physics, which is one of the things, the topics that we thought was particularly interesting, and that we had asked him in particular to talk to us about at this in this seminar. So Florian, thank you so much for taking the time. Great to have you here. Looking forward to your talk.
Okay, thank you very much, Dirk.
Stefan, are there logistical announcements on Q&A and so on?
No, don't worry about it. I'll message in the chat. Just everyone feel free to ask questions and use the chat if you have issues with the microphone.
Okay, super. Thank you.
Okay, very good. Okay, I think everyone can hear me all right, I hope.
Yep.
Thank you very much, Dirk, for introducing me. Thanks for giving me the opportunity to speak to you guys. This is a topic that I hope will resonate with many of you, and I will be excited if we can find connections between your research and what I'm going to present here. This is fresh off the press, so to speak. It's on the archive as of this morning. And so I really value your feedback. So the title here is Physical Self-Learning Machines, and I will explain what I mean via Hamiltonian echo backpropagation. And I also need to explain what I mean as I go along. But the starting point, oopsie, so I have a delay here. Okay, the starting point, the background is, of course, what you all know. There's a revolution going on in computer science affecting many other fields of technology and science, and that is the deep learning revolution. So deep neural networks bringing unforeseen power to information processing. And it started, let's say the revolution was kicked off, you could say, in 2012, when in this famous ImageNet competition, deep neural networks for the first time beat out all the competition. And after that, it has always been neural networks that were the winners in this famous contest. Now, going forward, say 2017, another milestone, deep neural network based program was able to beat the human masters of the board game of Go and other games, actually. And then I just list another example, 2020, one of these gigantic natural language processing neural networks that can read and to some extent understand text, and then say, if you tell them, it can write a new story that most people would not recognize as written by a computer. Now, the background of all of this is, of course, two things. First, the availability of big data sets on which to train, and here the internet definitely helped. And the other thing is raw processing power that you let loose, in addition, of course, to some smart conceptual developments. Now, what I'm plotting here is the kind of Moore's law plot that you see in many fields, and in particular also in this field of machine learning. So that displays the size of neural networks as measured by the number of trainable parameters inside the neural network as a function of time. And I just put two reference points on this log scale. One is the network that in 2012 won the ImageNet competition, and the other is this very recent natural language processing type of network with more than 100 billion parameters. So given this scaling, it's very natural to ask, and of course many people are asking this question, including you, can we build a better hardware to address the urgent need for this increased processing power? Hardware that would be very fast, highly parallel, and very energy efficient, because that's obviously a challenge here. And so the answer could be that you invent new processing paradigms that are maybe more closely related to how the brain works, because you also realize that much of the success in neural networks does not require you to make things at the utmost precision. There's a certain fuzziness and robustness to this way of information processing. Maybe you can exploit that, and maybe you can take inspiration from how real neurons work, or employ any kind of physical system for this task. And so one particularly promising platform for neuromorphic computing that I want to mention right away, also of course because it ties you to your research, is optical neural networks. So that kind of research started already early on in the 80s. And I will comment in particular on this pioneering paper by the Psaltis group a little bit later on. But I also list here several other papers that appeared over the years, many experimental, some also at the moment still theoretical, that have tried to use the obvious advantages of optical, to explore the obvious advantages of optical neural networks, like very highly parallel processing and possibly low energy consumption. Okay, but now let's zoom out a little bit, and let's not focus only on optical neural networks. Let's just say we have an arbitrary nonlinear physical system, and let's view it as an information processing device. So there will be some input that you feed in, and after some while it will produce some output. This input-output mapping is something you want to train eventually. You want to be able to change in order to get your desired input-output mapping, for example, recognizing images. And to that end, inside this machine, inside this device, there need to be some learnable parameters that can be adjusted so as to change the input-output mapping. Now, to make this a little bit more focused, what we will be talking about, and also to introduce the language that I'll be using in the rest of the talk, we imagine, let's say, adopt the language of wave fields. We imagine some field psi being fed into the device, propagating through the device, suffering some nonlinear interactions and so on, and then finally being emitted out of the device, and that corresponds to the output of the device. So that would be psi. Sometimes I call this the evaluation field, but I should also remark here already, when I talk of fields, in reality, this could be any kinds of degrees of freedom of a dynamical system, just for simplicity, a field. And then the dynamics of this field will be influenced by our learnable parameters. I call them theta. That's a standard notation also in the field of artificial neural networks. There will in general be many, many of those, as we have seen, billions possibly, and they affect the nonlinear dynamics of the evaluation field. Now the question, the obvious question is, how do we train this? How do we update the learnable parameters theta to get the desired input-output relation? And there is one naive, obvious answer that will always work, but in a moment I will make the point that it's not efficient. This obvious answer is the following. You just change any of the learnable parameters a little bit. You see how the output changes. You figure out whether that goes into the right direction. If yes, you keep that change. Otherwise, you change into the opposite direction. Now this works, but it's not the best thing you could do. First, it will require external processing and feedback, which may already destroy some of the advantages you might have hoped for in terms of processing speed and so on when you're using this physical information processing device. So that's one thing. The other thing is that the number of learnable parameters is very large. And if you apply this very naive approach, then you would have to change every one of the billion parameters a little bit in order to figure out what's the corresponding change of the output. And that's obviously inefficient. So how to do better? Well, let's take a lesson from artificial neural networks. Here's a representation of one where it's arranged as usual with neurons compiled in layers. You will feed in some input, let's say an image, into the neurons of the lowest layer. Then step by step, it will be processed by a sequence of linear and nonlinear operations. And finally, you produce an output, which again depends on parameters, here again called theta, which in a neural network would be the connection weights. And then again, the same question arises: how do you adjust those connection weights? And the most naive version, of course, as I just explained, would be to apply a small change, see what that means for the neuron values upstream, and then finally you get the output and you compare that to the desired output, and you see whether you're going in the right direction. This is inefficient because it scales with a number of parameters in your neural network. There's a much, much more efficient way, of course, that people discovered already 40 years ago now, which is you look at the output, you compare it with the desired output, that generates a kind of error signal that tells you how far off are you from the correct output. And then there is a very simple technique how to backpropagate this error signal layer by layer. And in a single backward propagation pass, you will obtain the correct required updates for all the learning parameters simultaneously. So the price you pay is the same as for a single forward pass. There's a single backward pass, and you know all the updates that you need. So that's backpropagation. And so the question is then, how can we build not just any physical learning machines, but physical self-learning machines? So what I mean by that is you would have completely autonomous training, no external processing or feedback is needed, except of course you have to feed in the inputs and the corresponding outputs, but no feedback and external processing is needed to update the parameters. So this update is supposed to happen by some physical dynamical process. And so both some version of physical backpropagation and some version of a physical parameter update should happen automatically by the dynamics of the device. So that will be the goal that we are targeting here. Now, to put our work into context, here's, so to speak, the landscape of neuromorphic computing. There's one big first distinction that I want to make. It's between heuristic approaches and optimization approaches. Optimization approaches are the ones I want to be talking about. They correspond to the whole field of artificial neural networks. So there you have a target function that you want to minimize, which is the deviation from the desired input-output mapping. There's the other domain that I will not be talking about of heuristic approaches, where you are really very closely inspired by how your brain works. Say you build physical models of spiking neurons, and then you have some ideas of how learning rules could work. This is more heuristic. There's usually not a very solid mathematical foundation as to whether this learning will succeed or what the machine will be doing. It's a very interesting subfield on its own, but I will be concentrating on optimization. Now, among optimization, again, you could just be building a nonlinear dynamical device as an information processing machine and then use, for example, feedback to update your parameters. That's fine. You could also already invent some version of physical backpropagation, and there are a few examples of that, and I will comment on one, probably the most successful. And then there is the even smaller subset of self-learning machines where the physical dynamics not only produces the backpropagation, but even the required physical parameter update. So you really do completely without feedback. And then in our work, what I will present to you is what we believe is the first example where we have invented an approach where completely independently of the details of your Hamiltonian, you can have a self-learning machine. But before I go to what we are doing, I want to comment on this really pioneering work by the Psaltis group. So that started at the end of the 80s. And it's quite amazing because this work is conceptually more advanced than many even of the theory papers that you would read nowadays. So I think this work really deserves a lot of credit, more than it obtains so far. So in a nutshell, what they have is some nonlinear optical device. The details do not now matter. They send through a strong forward wave that does the input-output mapping. Then they compute the error signal, so something connected to the deviation from the desired output. And based on that, they send backwards through the device a weak backward error wave. And now they have a very particular scheme. They make sure that the transmission of the forward wave as a function of power, let's say, has the standard nonlinear behavior that also can be encountered in artificial neural networks, where this is called the activation function. So that provides the nonlinear information processing. So that's the nonlinear transmission of the forward wave. At the same time, however, they engineer their device in a particular way that the transmission of this weak linear backward wave depends on the power of the strong forward wave in such a way that it mimics, at least approximately, the slope of the transmission. And that gives you exactly the right dynamics that is needed to realize a physical version of backpropagation. So that's optical backpropagation. So you're generating at each point of this optical device a signal that is proportional to what you would also get as your backpropagation signal in an artificial neural network. And then there's an additional step. So instead of measuring this and then feeding back on the learnable parameters, which is actually one of the things they also tried, they at least invented one version where you would take the overlap signal between the weak backward wave and the strong forward wave and use that overlap signal to change a certain hologram in which you encode your learnable parameters. And in that way, this becomes what we would call a self-learning machine. So both physical backpropagation and physical parameter update. So that's quite an amazing work. And they implemented these things at least partially experimentally in the 90s. Now, I want to come to our more general scheme, which we termed Hamiltonian echo backpropagation, and you will understand later why this name makes sense. But I want to start out with a basic idea. And the basic idea is related to what I just told you about, in the sense that we will also be talking about time reversal, about a backward propagating wave. And that's not surprising because that's a basic zeroth order idea of backpropagation itself. So consider a nonlinear wave field, psi. It propagates somehow, undergoes very complex nonlinear dynamics, here plotted in a space-time diagram. And now imagine that at some certain time, I'm able to completely time reverse this wave. So in a complex notation, this might mean I take its complex conjugate and I let it continue in its propagation. But what will happen is that as long as the underlying Hamiltonian was time reversal invariant, what will happen is that the wave refocuses back on itself. It just retraces all its old step and will re-emerge in the shape of the initial wave packet. So that will happen automatically. So that's an important ingredient. And now let's ask, okay, if I want to use this as an information processing device that I can train, probably this wave propagation depended on some parameters, some learnable parameters, theta, that I can change. So the question that I can ask if I want to train is, well, what would happen if I perturb these trainable parameters just a little bit? How would that affect the wave propagation? And well, as always, if you perturb a wave a little bit, then you will have a small linear wave signal, a perturbation riding on top of the strong nonlinear wave field. And it could look as the one shown here. So some source emits a small perturbation wave. Now that would just lend itself to the naive approach of training that I introduced in the beginning. You could perturb at any possible spots in the device and always record what is the resulting outcome, and then you see how you would have to change all these parameters. But we want to do something different. We want to inject a perturbation at the point in time at which we also time reverse the whole nonlinear wave. And so that means the perturbation rides back on top of this backward propagating nonlinear wave. And what will happen also to this perturbation is it also will refocus on itself. And the question is now, okay, in order to turn this into a physical learning procedure, how should I choose this perturbation? I should obviously not choose it in an arbitrary fashion. And so to give away the main story already here, but don't worry, I will explain it in much more detail later. The small perturbation that we want to inject is exactly this error signal that depends on the deviation between the desired output and the output that the network or that the physical learning device currently produces. And if we do that in just the right way, then I claim that the physical dynamics, if we do it right, will produce a training update that is exactly the one that we would need, that you would also expect in training an artificial neural network. And it is, of course, my task to prove to you that this is really true. At this point, I want to pause a little bit. I told you about this really pioneering work by the Psaltis group, and so there's always a danger. I don't want to trivialize our own work, of course, but on the other hand, it probably helps you if I compare and contrast our work with their work and do it really by boiling it down to the bare essentials. And I hope you can still spot a difference. So in the Psaltis work, you had a strong forward wave, and propagating on top of that, counter-propagating is a weak backward error wave. In our work, if you spot the difference, both waves are backward propagating. So there's a strong backward propagating nonlinear wave, and on top of that, there is a weak error wave signal. So that's the main difference. But this difference, as simple as it sounds, has very drastic consequences, because in their case, they had to really engineer the forward-backward transmission and also to engineer the update mechanism in a peculiar way to make this work. And so if you wanted to, for example, translate their ideas to any other physical system, you would have to start from scratch, basically. In our case, I will show you that this will work completely independent of the details of the Hamiltonian. Okay. So now let me move a little bit to the math behind this to convince you that this really works. On this slide, I just introduce first the players. So the players are the evaluation field psi. Think of the thing that you inject at the input, that you observe at the output, and hopefully it implements the correct input-output mapping, and it's undergoing some nonlinear dynamics. At the same time, it's coupled to what we call a learning field theta. And it's really a two-way coupling. So psi can act on theta and theta can act on psi, and that is really important for the whole thing. And then below that, I show a timeline of events. So at first, we send in the input, then say, it's always good to think of a wave field. It moves through the device. That's the forward pass. You receive the output. You produce the time reversal operation, and you also inject the error signal that I was talking about. Then you have the backward pass, which we also call the echo. And then finally, this will have resulted, and that's my task to show you, in the correct update of the learning parameters. And all of this is supposed to take place in a purely Hamiltonian system with a time reversal invariant Hamiltonian. Okay, so that's the setting. Now, again, if you have questions, please ask me at any time. I don't want to lose you at any point. So if you have questions, please ask me. Now, what do we want? What's our goal? As in any of these optimization approaches, you phrase everything in terms of an optimization problem. So you have a cost function, which tells you about the distance between the desired output and the correct and the actual output of the device. So in our case, I would say we have psi target, which is the desired output, and psi of 0, which is the output of our device. The points in time are chosen such that 0 is just at the middle of the whole time sequences. So it's just after the forward pass. This is when you get your output. That is what I call a sample-specific cost function, in the sense it measures the deviation for this particular input-output pair. And finally, you will average over that to get the overall cost function. You can rewrite this in an interesting way. You could say that I could write this in terms of the input that I sent into the device, psi of minus t, sent into the device at an earlier time minus t. And then, of course, it will also depend on the learning parameters, theta, and on their values that they have at the beginning of this forward pass. I'm very specific here because the interaction really goes two-way, and possibly even the learning field evolves during the forward pass. So I want to be precise here. But what we see here is already the cost function does, of course, depend on the learning parameters, just like for any artificial neural network. And that's why optimizing, minimizing the cost function means choosing the right learning parameters. Okay, so that's the cost function. Goal is to minimize this cost function by using physical dynamics. And we want to use the physical dynamics both to produce the correct backpropagation, which gives you this gradient of the cost function and evaluates it for every possible parameter in the device simultaneously in an efficient manner. And then to actually produce, using physical dynamics, the stochastic gradient descent update, which is this step that you say the new parameters are the old parameters minus the gradient, because that will take you downhill, and then eventually you end up in the minimum of the cost function. Okay. So coming back to the story that I tried to visualize with the wave fields, there are two ways of looking at this problem. The way that teaches you what you would want to do is that you say, okay, imagine I change my learning parameter a little bit. What change does this induce in the cost function? And then, of course, I want to update it in just such a way to move down the negative of this gradient. Okay, so that's what you want to do. But in order to turn this into a physical procedure, I claim that what you should do is to inject this error signal, so the derivative of the cost function with respect to the output value of your field psi. Inject this error signal, then let the physical dynamics run backwards, as it were, and then by the physical dynamics get your correct update. And that's what I want to show now. Okay. Just quick words to set this up. It's very convenient in all of this to adopt complex notation. Actually, I already smuggled it in before, but for any Hamiltonian system, you can put the coordinate and the momentum as real and imaginary parts of a complex number, not only for fields. You would rescale them properly to have the same dimensions, of course. And for our context, it's especially convenient since we want to describe time reversal operations, and then you just need to complex conjugation. And then also, since these two fields, psi and theta, are interacting anyway, I will combine them into some capital phi, which makes some notation easier. And then taking all of this together, the full Hamiltonian dynamics can be written in this one line, which looks a little bit maybe like a Schrödinger equation. So I times the time derivative is the gradient of this Hamiltonian with respect to phi star. So that's just very formal, but it makes life easy. Okay, so now let's look at the forward pass only for a moment. I have my field phi. It's really this combination of all the possible fields in the device. It is launched at time minus t, and it evolves in some complicated nonlinear fashion until time 0. Now I want to figure out what happens if I were to change this field a little bit at the initial time. What would this mean for the values of the field at the final time? Because one part of this change at the initial time is in particular the possible initial change of the learning field parameters, and I want to figure out what they would mean for the dynamics. So since it's only a small change, I can linearize around the complicated background nonlinear dynamics. So there's this capital phi of t, which follows completely nonlinear evolution, but I'm looking now only at a small signal on top of that. So I can work with a Green's function. So I have my perturbed input injected initially. I apply the Green's function, and that tells me what this means for the perturbation of the output. This is a Green's function that still depends on the nonlinear background signal. So it's, so to speak, sample specific. For each training run, for each signal that I send through the device, it will be different. And so now I can use this relation to learn what this means for my cost function. Remember, in the end, I'm interested in how does the cost function depend on small changes in the learning parameter. And so the gradient of the cost function with respect to the values of the field at the initial time, that's what I'm interested in. That's what I need for the learning update. And if I plug in the expression above, I find, oh, this can be obtained by applying the Green's function to the gradient of the cost function with respect to the value of the field at the output time 0. And that in turn is easily obtained for the simple reason this may just be a quadratic deviation between the target output and the actual output. And so taking this gradient is just taking the gradient of a quadratic function. So that's easily obtained, but what I need is the left-hand side. And what I have in between is this funny, Hermitian conjugate of some Green's function. So the question now is, how do I turn this mathematical expression into a physical prescription? And so what I'm using here is something that I already indicated in this picture of the waves that are propagating backwards. And on top of this nonlinear backward wave, I have a small signal. Because it turns out that if I want to have this Green's function that seems to be going backward in time, what I can also look at is the Green's function, but now calculated for the echo field. The echo field being the time reversed evolution of the field, which is physically what I really literally get if I time reverse at time 0 and then just let the usual Hamiltonian dynamics take over. So the Green's function of any signal propagating on top of this strong backward echo wave, that's something that I will be able to implement physically. And so taking these steps together, what I found is that I can turn a mathematical formula that I need for my backpropagation update into a physical prescription. So at time 0, that's the time when I receive the output, this prescription says I need to inject an error signal that is easily obtained actually. And then I need to look at how the small error signal propagates on top of the big backward, the strong nonlinear backward echo wave. Okay, so let's summarize what we want to do. So I have undergone the forward pass that has happened already. I got an output. I now need to inject my error signal. So that would be the gradient of the cost function. And actually, physically speaking, it turns out injecting this error signal can also be understood as applying for a very short time a certain Hamiltonian, namely the Hamiltonian whose functional form would be equivalent to whatever cost function I have. That may sound a little bit crazy maybe, but if the cost function is simply the overlap between the correct target and the actual output, then it turns out applying this Hamiltonian for a short time means nothing but injecting the target wave configuration on top of my field. So it's actually not that difficult. So that affects this operation. So my field will now acquire a small injection of this so-called error signal. And then I still time reverse. This is the time reversal operation that I already introduced before. So what now happens is everything goes backwards, including the small error signal. And at the final time, if I introduce an additional time reversal, what I will end up with is this, this relation. So the final time field configuration is exactly the same as the initial time field configuration. That's because I had a time reversal invariant Hamiltonian, and at the half time point, I had this time reversal operation. But in addition, it has this extra contribution that came about by me injecting the error signal. And this looks very, very much to like what I really need for the stochastic gradient descent update. It's almost correct, especially if I now look at the particular component that is the learning field. It's almost correct, except not quite. It has this nasty I here. And this is not just some nasty mathematics. This is actually physics. What it means is that my learning field has gotten a kick in the direction of the learning update. So the momentum has changed, but now I need to turn this change of momentum into an actual displacement in the value of the learning field, in the value of the coordinate of the learning field. So there's still one slight additional step that I have to implement. But that is easy enough. For example, if you just have some sort of dissipation, maybe you can control it in a way that you switch it on now. Maybe it has been always there and was just weak enough. Then this dissipation will convert your momentum change into a displacement eventually. And so overall, we really end up with a stochastic gradient update. And all of this has been done via physical dynamics, and it works for arbitrary Hamiltonians. So I want to summarize this now. That's the procedure that we call Hamiltonian echo backpropagation. Forward pass, you get the output, you inject the error signal, you do the time reversal operation, backward pass, and then you still have this little decay step that converts the updated momentum of the learning field. So I have plotted down here the momentum of the learning field, or one of the many momenta if you have 1 million learning field parameters. In the forward pass, at some point the learning field, by its interaction with the psi, with the propagating pulse, will get a little kick. Okay. Then at the mid time point, we undergo the time reversal. So you just flip the sign of the momentum. Then as everything propagates backward, we get a second kick, actually in the same direction. But the very crucial point is this second kick will not be exactly the same as the kick we received in the forward pass. Why not? Because we injected this extra error signal. If we had not injected anything, everything would just cancel and you would be back at the beginning. But since it doesn't quite cancel, you get a learning signal and then you convert this into a displacement of the learning field. So that's the idea. Okay.
Could I ask a question? Sorry,
yes, please.
Yes. So I kind of know somehow how the neural net works, but I was just wondering here, for every parameter you want to learn, do you have to do this echo like a number of the parameters, or like you just do it once for the propagation?
Exactly, you do it only once. That's the beauty of it. So of course I draw a curve only for one of the 1 million parameters, but all of this happens simultaneously in parallel for all the parameters automatically. So it's really like in this backpropagation where also the expense is very small of doing a full backward propagation pass in the normal artificial neural network. So it's the same spirit.
I see, but I assume, so you just look at the outcomes of your backpropagation, and then I assume you have just single layer, right? This is not layers. So so like but isn't you have only one outcome? How did you got the, I mean, the derivatives of all the parameters? Maybe I missed a little bit in that part.
Okay, so maybe I can go forward for a moment and I then come back to your question, because I have a very simplistic toy model where I show how things work, and then we can discuss this again and maybe it makes much more sense then.
Great, thanks.
Okay, good. Okay, just quickly before I go to this toy model, I want to emphasize the universality of this training procedure. So all of what I described works really completely independently of the Hamiltonian of the evaluation field. So it can obey some complicated nonlinear wave equation, or maybe it's not even waves, maybe it's some mechanical system, which I will show in a moment. So it always works. It is also independent of the interaction Hamiltonian between the evaluation field psi and the learning field theta, which is very interesting because this plays even two roles. First, it will affect the input-output relation. So this tells me how the learning parameters enter in my nonlinear dynamics that produces the input-output mapping. At the same time, the same interaction Hamiltonian will also enter the update. So how the theta field is changed according to the dynamics of the psi field. And the same Hamiltonian enters both of these aspects and enters them in just the right way to make this backpropagation work. The only thing we need is time reversal invariance. So we could even treat these components like a black box. Maybe you don't even know the details of your system. Maybe you didn't even engineer it. It will still work. for the h theta, for the parameter, for the Hamiltonian of the learning field itself, we need a little bit more, because of course the learning field should be multi-stable. So it could take on this value or that value or that value, because that should eventually be determined by the learning itself, which value it will finally take on. So you need a degenerate ground state manifold. So you have to look for a physical system where that might be true. Also, at the end of the step, I already told you I need some dissipation. So maybe it's best to have controllable dissipation. But all the other details, again, are not important. And I even can show you a way of how to get rid of some of these constraints. You can also just say, okay, let me now average over time many training steps. I undergo this procedure, and let me look at the effective Hamiltonian only for the learning field, so to speak, the training field or the pulses that go through the device that has been integrated out, gotten rid of. I only look at the effective dynamics of the learning field, and I will find a very interesting Hamiltonian that consists of the bare Hamiltonian of the learning field, the Hamiltonian that somehow describes the dissipation. So I say there's an H bath, that's just the dissipation. And then on top of that, there will be the cost function Hamiltonian that I introduced before, now, however, averaged over many training samples. So what will happen is that without the training going on, your learning field has a degenerate ground state, so it can take many different values. It hasn't decided yet. But if you undergo this training procedure repeatedly, then this extra cost function appears, and that will break the degeneracy, and it will automatically drive the system to a minimum of the cost function. Okay. So now, now I come to my toy model example, and I hope it makes some things intuitively clear. This one has very few degrees of freedom, but I think once you've seen this example, it will also become apparent why and how this works for arbitrary systems. So this is a mechanical pinball self-learning machine. It has two charged balls. I call one psi because it's somehow the evaluation field ball. And that's the learning field ball theta, which can move on a rail, okay? And now I will inject the psi ball with a velocity that represents my input, yeah? And so it will undergo some trajectory as it moves through the device. It will also, because both of them are charged, give a little kick to the theta, to the red ball. So that starts moving as well. And now I'm at my midpoint in time. I have obtained an output, which may be the location or the velocity of this ball. I can note the output if I like. And now I will do two things. I will time reverse both the red ball velocity and the purple ball velocity. So that's the time reversal operation. And at the same time, I compare, say, the location or the velocity of this purple ball with what I would have wanted, what was my desired target output, and I will shift it a little bit or change its velocity accordingly. So that's injecting the error signal. And now I let the dynamics just proceed. I don't do anything anymore. What will happen is, of course, since I reversed the velocity, the purple ball will almost exactly retrace its original trajectory. Not quite exactly, because I also injected this little error signal. And so it will again give a kick to the red ball, but this kick will now be slightly changed. And because of that, even after the full operation is completed, the red ball still keeps moving, and eventually friction will dissipate this motion, but the red ball overall has been displaced a little bit, which will mean that the next time I send in the purple ball in the same configuration, it will encounter a different situation and will slightly better go into the direction that I wanted it to go to. Now, this is, of course, a super simple self-learning machine because it only has these 2 degrees of freedom. But it's already demonstrating that it's very universal. For example, I could have had an arbitrary nonlinear potential in which the purple ball moves. This all would still work. And now you can imagine that I would not just have this one rail. I would have several of these rails. I would have maybe this input signal would be represented by several purple balls or so. Everything would still work just as before, and everything would happen in parallel. So I don't know whether that made things clearer, but the claim is really everything happens via physical dynamics. And so there's no problem if I have more than one training parameter. Did that somehow give you an intuition that helps you
Yeah, this is
understand why
much
everything
clearer.
can work?
Thanks. This is much clearer compared
Okay,
to what
thank
I.
you.
Yeah,
Okay,
that's good.
very
Thanks.
good. Okay, so
May I interrupt here with maybe a related
Yes.
question? How does this relate to local minima in the optimization? Do we know that the training update won't force the parameters into a local minima?
that could always happen, but that's just the same as for any artificial neural network. So to speak, that's exactly the same problem that I could argue is there for any artificial neural network. So what people there have found is that if you have sufficiently many learning parameters, then, I mean, the saying goes that you typically rather encounter saddle points in this very high dimensional configuration space, and you typically don't get badly stuck in local minima. But I'm pretty sure that if I have only such a simple device with only one single learning parameter, then I can suffer very strongly from such local minima. That's also clear.
I see. Thank you.
Mm-hmm. Okay, so I need to watch the time a little bit, but I'm wrapping up just telling you a few extra things. So there are a few architecture choices regarding time reversal, whether you do it inside or outside for the learning field and for the evaluation field. So the standard approach would be you imagine you have your device, inside are some learnable parameters. You send in, maybe as an optical pulse or something, your evaluation field goes through the device, undergoes its nonlinear dynamics. You time reverse it by some phase conjugation mirror, for example. It goes back. There is all this coupled dynamics going on, and eventually you will have updated your learning field. This kind of setting, of course, reminds you very much of an artificial neural network because it has a kind of sequential structure. You go through from left to right and then back from right to left. So it's a little bit like a layered structure. You can have also very different setups where everything is somehow, where you don't even see any layers. So you could have both the psi and the theta completely inside the device. You somehow still have to inject your input signal. There are some waves that propagate. Then you're at the midpoint in time, you start to inject your error signal and you time reverse everything everywhere. The waves will somehow shrink again because they have been time reversed. So this is what's going on here. Of course, this is much more challenging to implement physically. It will probably, you will not be able to do it in a continuum material, but if you have completely different physical devices that are maybe composed of many discrete elements like microwave resonators or something like this, it could be achievable to have this going on. So it's just an example of a very different architecture. Okay, there's another remark I want to make coming back to the time reversal configuration that I talked about in the beginning. So typically we would imagine the learning field inside the device and the evaluation field is propagating through the device, being time reversed, tracing back its path, and then you see the next training sample and the next training sample and so on and so on. What we need is obviously that the theta learning field will be time reversed inside the device, so maybe that's a challenge. Also, we know already that we need to have a degenerate ground state manifold for the learning field. That I emphasized that several times. That's of course a constraint on the learning field dynamics. The funny thing is I can get rid of that constraint, I claim. And the way to get rid of it is to time reverse both fields outside. So think again of an optical device. That's a good way to think of it. And you send in both a pulse representing the training sample psi, as well as a pulse representing the current values of the training field theta. They both co-propagate, they interact in a complicated manner, and they will be both time reversed outside the device. And then you go back and forth. And while you are always injecting new training samples psi, you keep bouncing back and forth the same learning field all the time. If you do this, it turns out, then you can really have a completely arbitrary Hamiltonian for theta inside the device. And still, because of the multiple time reversals, you effectively get something like a degenerate ground state for theta. So you can even get rid of this constraint and you become fully Hamiltonian independent. Okay. Next final remarks. There are some ingredients here. Again, for artificial neural networks, there's the general backpropagation, but also there's the very specific ingredients like which activation function do you use, which network architecture, and so on. And so here, how to realize the learning field. Mechanical motion comes to mind because, for example, if you have molecules whose angle can be arbitrary, or if you have a nanoparticle that is levitated and can move freely, that seems like a nice degree of freedom to store information in, but it turns out to be very hard to time reverse. Now, oscillatory modes on which you have good control would be much easier to time reverse, but where do you get the multi-stability that you need for the learning field? And then the first thing that comes to mind is maybe you can employ a limit cycle, but you realize, oh, that only gives you dissipative dynamics. And finally, you figure out that if you couple at least two modes and drive them in the right way, then you can engineer a continuous degenerate ground state that you would need. So there's more of that in our paper if you are interested. Next comment I want to make, time reversal. This is a little bit peculiar operation. It's never purely Hamiltonian, but people know, of course, how to do it. For example, in nonlinear optics using phase conjugating mirrors. If you think of localized modes, what you would do is you apply some parametric driving to these modes and then some swap operation. And by that combination, you can really make sure that the final configuration of mode A is just the time reverse of its initial configuration. But interestingly, you always need another mode to play a part. This is because the overall operation is not purely Hamiltonian. And then finally, you know that most supervised learning applications really map from a high dimensional input like an image to a low dimensional thing like a label. So that's contractive dynamics. This doesn't square very well with Hamiltonian dynamics, which always conserves phase-space volume. So how to do this with reversible dynamics? And so the solution that we invented, if you really want this, is to have some ancillary modes. So the ancillary modes would also be injected in the beginning, say initialized in 0. They would interact with your field psi. And then more as time goes on, more and more of these ancillary modes would be split off, not take part in the interaction any longer. But importantly, they still get time reversed. So overall, you still have a complete time reversal invariant system, but still these ancillary modes, they produce something like pseudo dissipation, splitting off some of the energy as you do the evaluation dynamics. Okay. Quickly, numerical examples. You can try to learn an XOR function. That's basically practically the simplest thing you can train anything like a neural network on. So the B output should be A1 XOR A2. We would encode the input in the location of some wave packets, then they would undergo this interaction. And then finally, depending on whether the wave packet comes out at the top or the bottom of the device, that would represent B equals 1 or 0. What is most interesting here is not how this device eventually works, but how the backpropagation algorithm works. So here I'm showing the learning field momentum in a single training step, in a single forward-backward pass. And what you see is as the wave field psi propagates, it imprints a kind of signal on the learning field. Then as we are time reversed at the midpoint in time and the psi field propagates back, it even deletes some of the initially accumulated signal, but the deletion is not complete exactly because we injected an error signal. And finally, you arrive at what is really the learning update and which you needed. Okay. And so if you do this many steps, not only one step, but many steps, you can start out from a completely random learning field, and it will eventually emerge in a configuration that produces a machine that does what you want. You can see that the cost function as training progresses goes down in time. We even analyze what happens if you have a noisy time reversal operation. That of course makes it harder to operate, but you can average away the noise, so that also works. Here's a second example, much more ambitious. That's the famous handwritten digits. So you send in a picture of a handwritten digit. You want to figure out which one is it. You can build a kind of photonic neural network with several layers, and again, train this using the same procedure, say with current nonlinearities. And what we also investigated then is, say, what's the effect of the nonlinearity? And you find interesting things like you have to go surpass a certain threshold in nonlinearity to get the validation error to a very low level. So there's some interesting physics there. And then just finally, what are experimental platforms? Well, I tried to explain to you this is completely Hamiltonian independent as long as it's a time reversal invariant Hamiltonian. But so any platform that has some nonlinear dynamics would be nice, but nonlinear optics recommends itself. Either nonlinear optics, say in microresonators or so, or maybe the combination of optics and mechanics. So cavity optomechanics is also can also produce nonlinear classical dynamics. So maybe that's also a good alternative. And then if you want to have a lot of control, one platform that also comes to mind is superconducting microwave circuits, simply for the reason that all this effort in building quantum computing platforms has now given people such a great level of control that this could be a platform, even though, of course, admittedly, the bandwidth is much less than for optical waves. And then finally, you could think of nonlinear matter waves or even spin waves, but there you need to look at it very closely, because what you do not want to do is break the time reversal symmetry. So only some scenarios will work. Okay, so that brings me to the summary. I think, so the main message is really now there is this approach that is completely general in the same way that stochastic gradient descent and backpropagation in artificial neural networks were completely general. And so that should open up many possibilities to investigate various platforms. And there we are just at the beginning. So basically that's the next steps that we have to take. Well, thank you very much.
Very, very interesting. Thanks very much, Florian. So we have some time for questions.
So everyone, just feel free to unmute. You should have the admin permissions for that now. Maybe I can start with a question. So this theta field needs to, those are the parameters that are put in when setting up the computation, and we need to update them. And I think I understand that those do get updated each step, but when we're done with the training, is it obvious that we can always read out the theta parameters we obtain at the end, so that next time we don't need to do the training from the very beginning?
Okay, that's a very smart question. So here, of course, I assume that the theta parameters are stable to some degree, but you may be right. Maybe there are stable, say, I don't know, on a time scale of a few seconds, which is maybe good enough to do some validation, but maybe not on a time scale of several hours, which you might want to have. That's a very good question. We actually haven't thought about that. That will depend now very much on the platform, of course, how much access you have to these theta parameters. So basically what you are asking is something like, would there be a way, for example, even just to copy? Yeah? So basically I have two devices here. This one is already trained. Now maybe there's a smart way of sending through some extra fields in order to copy the parameters to a second device. No, but I simply haven't thought about that.
Yeah. On one hand, I guess venture capital funds will be super happy that you have digital right management and no one can copy your hardware. On the other hand, I kind of hope it is copyable.
No, that's a very fair point. Yes. So for all of these platforms, so where did I talk about things? The physical, yeah. So the ingredients I talked about here. So Well, so in the end, of course, you will have stored them in some, say, micro resonators, and maybe you have some extra access line, and then you will find ways to read them out. But I agree, if especially you want to scale up the number of trainable parameters, maybe you don't want to engineer things too much. And so that, yeah, that's an interesting question, how to copy them or how to read them out. Okay, food for thought.
Thank you.
I just had
this was really interesting.
Oh, sorry, I had a quick question. So you said mechanical motion was hard to time reverse. I was just looking at this figure, thinking of previous work I'd done in molecular physics. So if you think about the rotational degrees of freedom of a diatomic molecule that can be coupled to a strong laser field, for example, that's obviously that's just purely Hamiltonian dynamics, right? It's Schrödinger equation in the rotational degree of freedom. So yeah, I was just wondering.
And you say there it worked somehow to time reverse the motion?
Well, it's purely Hamiltonian dynamics that's governed by a strong laser field that you apply, and you can do things like aligning molecules, and you have echoes as well, and
well, I'd be absolutely interested to look into that. So this fact that time reversal is difficult, we discovered in a very painful way. I also imagined initially, oh, this should be easy. For example, if I have a charged particle, yeah, I just apply a magnetic field for half a cyclotron period, and then I will have reversed the velocity, and it's great, yeah. But in this case, if you analyze it more carefully, you see, oh no, by switching on this time reversal magnetic field only for a short time, I will automatically induce, you know, a time-dependent electric field, because any time-dependent magnetic field will induce a curl electric field, and that suddenly spoils it. And then we looked into it in more detail, and then of course at some point it hits you, oh, a time reversal does not preserve the Poisson brackets. It's a volume preserving operation in phase space, but it does not preserve Poisson brackets simply because you flip the momentum. So what you can definitely not do is with a Hamiltonian, whether it be time reversal invariant or not, that doesn't matter. With a Hamiltonian, you cannot just flip the momenta and not do anything else. So that's why what I showed down here is a way out of this, where you bring in an ancillary mode and then you dissipate that. So in total, it's still Hamiltonian dynamics, but on the mode of interest, it is actually time reversal, and it doesn't run, it doesn't violate anything. So I would be really interested in what you mentioned to analyze it. Either what they mean by echo is maybe a little bit different from what we mean by echo, or maybe such another degree of freedom will get involved, and then it starts to work again. But okay, so maybe I can somehow contact you, or you can contact me, and I would be very interested.
Yeah, I have to say this is quite a few years ago that I did this, but I had this spontaneous association with that. I'd also have to look into it again. Okay. But yeah, thanks for the answer anyways.
I have a little bit follow up on that. So like I assume like what you can do, you have an input field and you have some auxiliary line, which is your theta parameters. And then you can engineer whatever Hamiltonian to entangle them like to a higher order. And then you can time reverse that Hamiltonian, presumably, without have to paying the thing you're saying. And then what the goal is, like you just look at what the theta parameter, like a zero line, how much they moved, right? How much they changed, and you try to do the feedback again. That's my guess. So this is a little bit related to Stefan. I think like one of the things I'm thinking is like when people doing all this like digital computer self-learning, they try to know what the parameter theta is and try to find them like a global minimum, global maximum of the cost function once you learned it. How would you like propose in your case like for this quantum system to like, I mean, once you learn the system, how did you find the like, let's say the global minimum maximum like you are looking for at the end?
So first, let me just state right away, we are only talking about classical systems here. That's actually also important for the time reversal operation because, again, it's not a unitary operation. And then I think the answer is the same as I think it was asked before. So the cost function, the issue that the cost function might have local minima, that this issue we do not pretend to solve. It will be exactly the same issue as for any artificial neural network. And so we just judging from the success of artificial neural network training, we see that if you have sufficiently many trainable parameters, I don't think this will be an issue of getting stuck in local minima. But we do not pretend to this will be exactly the same problem or absence of problem as you have for artificial neural networks right now.
I see. So you basically treat it as a black box, like so you put whatever the input, then you want whatever the output like you desired for. Instead of like you are looking for like you try to optimize, let's say, a financial market to get the best trade today.
Yes. So yeah, it's an optimization problem, but an optimization problem for a particular task, which is the input-output mapping. So I'm not here, I'm not using this for any other optimization problem. So that's also why I hadn't thought of how to extract the theta, but still the point was well taken by Stefan that maybe in the end I want to store them somewhere else in a more long-lived memory.
Maybe another related question. Say that the network I want to do is not just the Hamiltonian dynamical system. I am really attached to using rectifying linear units. Is that just forbidden in this system? I'm asking because they're not a bijection. They don't map one-to-one.
Yes.
They lose information.
Okay, so we thought a little bit about this. So one solution we came up with, or Victor actually came up with, is already at this point to use ancillary modes. So in the interaction that produces this nonlinearity, to also come in with an ancillary mode, and then I can basically do anything. The price is, of course, that for every such nonlinear self-interaction, I will need another ancillary mode. Yeah? And then it will depend on the platform whether you're happy with us or not.
So if that works, why don't people with classical neural networks just never cut down the number of dimensions? Why do we? Yeah, how is that? Why is that not done in classical neural networks?
Oh no, but so in classical neural networks, of course, there's a small subfield of invertible neural networks, which are useful for some tasks. For example, you can try to map an arbitrary distribution of input samples into a Gaussian normalized distribution at the output, and then a sample from that distribution and go back to the input. And so there are very interesting things that you can do. But for all the normal classification, of course, it would not be needed. And since you don't pay any price in that case for using something contractive, you're happy, right? With the ReLU or sigmoid or whatever.
Yeah, I see. Thank you.
Okay.
Although it would be interesting maybe to see what actually would be the states of the ancillary modes if you actually did carry it through. It probably carries some contextual information that normally we discard.
Yeah, so I guess this would then be, at least that's one version, so to speak, of these invertible neural networks. And I can show you, I can just briefly tell you about an example that we did in another context. So there's one version where you have the high dimensional input like an image, and then you have a low dimensional output, which may be the label or something. Plus you supplement this output with, so to speak, a large number of ancillary output labels, where you just demand that they be, in the end, Gaussian distributed, and you demand nothing else. So to speak, all the superfluous information will be rediverted to these extra output labels. And this can be quite interesting, and especially interesting for if you want to sample. So for example, you want to sample, give me an image of a cat. So cat is the label, and you put in some extra random Gaussian numbers and you get, so this is actually a way of having generative networks.
Yeah. Okay.
May I ask you one final question here? So like, I think this is very nice work, but I want to be a little bit critical. So why this is better than the classical neural network? Like, because you're learning something, you're still learning something classically, I assume, or?
No, yeah, but no, so the whole point is here, we want to have a physical device that uses the rapid processing, high parallelism and so on. People are, of course, already working on those devices, but then always training is somehow a bottleneck. Maybe sometimes you don't care, maybe training doesn't need to be efficient because you have the standpoint that you train in some cumbersome, slow way, and then later, so to speak, in the field, you just want to be very rapid in your responses. So maybe you don't care about training. But if you also want to have training be very fast, maybe it's smart to do it completely by physical dynamics. And so this is what we offer.
Great, thanks.
Okay, there were tons of questions. I know that there are more, but maybe we ask people to email directly to Florian. And
Okay, good. Great.
we probably should move on for now. So thank you again, Florian.